Welcome everyone, and thank you for attending our webinar. During the presentation, if you have any questions, please type them into chat and they will be answered after the webinar is over. Enjoy the presentation.
Hi everyone, my name is Harold Scarborough. I'm the Technical Project Manager for ALS Oils and Lubricants. I've been in the oil industry for roughly a decade and I've specialized in the analysis of lubricating oil, fuels, and coolants. I have a background in data analysis and a degree in biochemistry from the Georgia Institute of Technology. In this webinar, we're going to be discussing why do companies extend your oil drains? What are some of the problems that can arise from extending those oil drains? What are the factors that affect extending oil drains? How you can measure your oil's health with oil analysis, how your oil's health declines over time, and how you can track the decline from a top-down view. And finally, we'll look at how you can use oil analysis to safely extend your oil drains. But before we get into all of that, we need to touch on a big reason this topic is becoming more prevalent and why you should be paying attention to the topics covered in this webinar. We have heard countless news stories on the price of gasoline since the beginning of the year. It is no secret that the volatility in geopolitics has an effect on gas prices, but an often overlooked area in the media is lubricating oil. What you see on screen is the price index estimate of two types of lubricating oil since the beginning of 2026. This public data was pulled from the Bureau of Labor Statistics Producer Price Index for lubricating oil and grease manufacturing, the Federal Reserve Bank of St. Louis, and Jobbers World lubricant reports. It shows a relative price point increase since January of roughly 13% for industrial oils and 15% for heavy-duty engine oils. Regardless of the reasoning, price increases at this level would make any company start to consider how to cover costs and overhead in lubricating oils. Indeed, many customers have been already starting a trend towards silently extending their oil drains. Doing so without understanding the mechanisms that limit these extensions, unfortunately, is a recipe for disaster. But there are many reasons one would want to extend their oil drains even outside of the price increases. For one, it decreases waste disposal costs. Whenever oil is changed out, it must be disposed of in a responsible manner, whether that be through oil recycling, disposal. These oils need to be transported and dealt with. Reduction in the frequency you have to do this is a save on bottom line relatively quickly. Likewise, if you are decreasing the amount of oil you're using, you're going to find that the overall cost of your lubricant going down as well. For example, if you extend a drain interval from, say, 500 to 1,000 hours, you're effectively halving the amount of oil consumed each drain interval. In a similar vein, decreasing the amount of oil changes is going to decrease your scheduled maintenance costs. The same increase from 500 to 1,000 hours will also decrease the amount of time spent performing full oil changeovers. Scheduled maintenance can be loosened and shifted around to provide for less overtime. Finally, environmental concerns should also be taken into account. If you live in a state, province, or country with carbon footprint regulations, the decrease in oil usage can increase the environmental sustainability of your company. These are just some of the benefits, and we can go into more, but there is somewhat of an elephant in the room: reliability. Increasing drain intervals is a goal that both consumers and oil producers alike strive for, but you cannot increase them indefinitely. Increasing the amount of time the oil is in a unit will increase the stress on that oil and can lead to significant reliability outcomes. Entire units can have their lifespans drastically reduced, and some can even be rendered completely inoperable by overextended oil. So, how can you tell what is going to happen? First, we need to discuss some of the variables that can affect oil drains. So, number one is operating conditions. Now, let's say you have two trucks. Same type, same engine model, same oil being used, everything is the exact same. The only difference is one is operating in South Georgia and the other one is operating off the coast of Nova Scotia. Now, I'm from South Georgia. I know down here it is humid, it is hot. There's the clay that just gets on everything, and there's more swamps than there are people. I have not been to Nova Scotia, but I'm going to go out on a limb and say that the operating conditions are going to be a little bit different. Those two trucks, even though they're exactly the same in every regard, except for the fact that they are in different locations, are going to have drastically different stressors that are put on them, and the oil is not going to age at the same rate for either one. Compartment types are another major area of consideration. You can use the same oil in two different compartment types, and it's going to age differently depending on which one it is. And even if they are the same compartment type, older models can perform very differently from their newer counterparts. It pays to know how your individual equipment works. Similarly, equipment age has a massive impact on how it performs. A transmission that's just fresh off the factory line is going to be operating at ostensibly peak efficiency, whereas that one that's been sitting in your tractor from 1985 is going to behave completely differently. Fuel type and quality matters a lot as well. For example, natural gas engines tend to run much hotter than diesel engines. This increased heat is going to drive processes that wear oil out. So the drain intervals are going to be completely different for a gas engine and diesel engine, even if they're using the exact same oil. And finally, lubricant selection is probably the biggest impact on your drain intervals. Depending on what kind of oil it has, be that mineral, semi-synthetic, synthetic, the average time until the oil degrades can be drastically different. This can vary between brands, product lines, even suppliers as well. Understanding what your lubricant is and is not capable of is going to alter how you manage your oil changes. And these are just some of the factors influencing how long you can run your oil. There are many, many more, but these are just some of the major factors influencing how long you can run your oil before it wears out. But how can you actually measure your oil's health? Well, I wouldn't be very good at my job if I didn't promote at least a little bit of oil analysis. Contrary to pretty much every post-apocalyptic movie in existence, oil does age and does have a shelf life. These changes can happen chemically and physically, and I'm sure you've seen the physical ones before with your oil turning black or it's smelling burnt, something like that. But chemically, a lot of times these changes are hidden from human senses. This is where you have to use oil analysis to confirm your oil's current health. The big tests in an oil analyst's arsenal for determining oil health are acid number, base number, viscosity, oxidation, and contamination. All of those contribute massively to understanding your oil's longevity, and only when they're taken all as a whole in concert do they paint a clear picture of what is going on in your oil. Now, we're going to go through each one and discuss the mechanisms behind the oil aging, what the tests show, and how you can interpret them. Well, first up is oxidation. Unfortunately, you guys, my background is in chemistry, so you're going to have a brief refresher, but I'll try to make this as painless as possible. Oxidation, in chemistry terms, can be summarized by somewhat apropos mnemonic device oil rig. So oxidation is losing an electron, reduction is gaining an electron. Now, there's a different interpretation for lubrication, where oxidation is gaining an oxygen and reduction is losing an oxygen. When carbon chain molecules that make up oil undergo oxidation, radicals are formed. These radicals continue the cycle, proliferate, and accelerate, which in turn causes the breakdown of oil. Before we get into the cycle and how it works, we need to address what lubricating oil actually is made of. At the bottom of the page, you can see a long chain of carbon atoms bonded together with their respective hydrogen bonds. This basic structure is an alkane, and all oil is made up of chains that are, somewhat similar to this and can come in varying lengths and configurations. But we're going to use this one as a simplified version to show the chemical reactions going on in the oil and to not make this more complicated than it already is. Additionally, I've highlighted a section of this chain as an R group, and it will just basically is an abbreviation for the rest of the molecule, so I don't have to keep drawing it over and over again. So whenever you see that R group, just know that it is a long carbon chain. And also, please do bear in mind this is a massively simplified version of what is actually happening. There are many different ways that can play out from a molecular standpoint, but we'll just be covering the basic reaction. All right. That out of the way, let's do some chemistry. So first we see that original alkane that I mentioned on the previous slide. As I said, you can see that R group sort of coming off the side. Just remember, that is the rest of the molecule sort of branching out into infinity. And then we have this little section that is the 3 carbon atoms bonded with their hydrogens. Now I want you to pay attention to that hydrogen atom there, because that is going to be the start of the reaction. That hydrogen atom, and really the molecule as a whole, when it is exposed to heat and maybe a catalyst, it breaks that hydrogen bond. That hydrogen is gone from the molecule, and you're left with the same molecule with an unpaired electron next to that carbon. Now, this is what is referred to as a free or reactive radical. What makes this molecule reactive is that free electron. It really does not like to be unbonded to anything, and it'll search for anything that it can bond to. Unfortunately for you, one of the things that it wants to bond to is readily available in your compartment: molecular oxygen. When this free radical comes in contact with molecular oxygen, it forms a different reactive radical, a peroxy radical. This is the same kind of chain with just two oxygens bonded to that carbon chain with a free electron at the end. Now, again, this is a reactive radical. It has an unpaired electron. It wants to bind to something. So what happens when that reactive radical meets another R group, another long carbon chain? That's right, it steals its hydrogen. So this is the end of the first stage of oxidation. You end up with another reactive radical and what is called a hydroperoxide. From one carbon chain through this first stage of oxidation, you end with a completely different molecule and another reactive radical. So what's going to happen to that reactive radical? It's going to go right back to that first step and propagate the exact same reaction over and over again. And unfortunately for you, this is not the end of the story, because that hydroperoxide that was created, it is not a very stable molecule. So let's take a look at that hydroperoxide. It's a simple carbon chain with two oxygens and a hydrogen bonded at the end. Some of the more astute chemistry enthusiasts might already kind of see where this is going. Like I said, this hydroperoxide is not very stable, and it will commonly undergo decomposition, which is basically just it breaks apart. Forms new molecules and more different reactive radicals. This can present itself in many different ways, but right now we've got it decomposing into two reactive species. Remember, both these species in this decomposition have free electrons. They are reactive. They want to bind to things, and they're going to do that. At the end of the second stage of the reaction, you're left with an alcohol, not the fun kind, a chemistry kind, a water molecule, and three more reactive radicals. So, taking first stage and second stage together, you started with a single carbon chain, and all you needed was heat and oxygen, and you end up with an alcohol, a molecule that does not what a normal carbon chain does, water, which we know water is not great to be inside of an engine or any compartment, and three reactive radicals. Each of those three reactive radicals is going to do this process again. So if you're looking at this from a expositional standpoint, one oxidation reaction begets three reactive radicals, which then beget 9, and so on and so forth. This is why oxidation is such a problematic process. It's exponential. It will continue on like this until the carbon chains in your oil are destroyed. Luckily, oil manufacturers have devised ways to delay this process and interrupt the feedback loop. This is accomplished with antioxidants. Antioxidants come in many different forms, but they're there to slow down this reaction. Each type of antioxidant, whether that be primary or secondary, break this oxidation reaction at different steps. Now, I want you to be aware that this does not stop the oxidation reaction. This just breaks a part of the chain. It slows it down. There are still going to be oxidative products and reactive radicals that are formed from this. Antioxidants just slow the process. Another thing to understand about antioxidants is that they are finite. There is only so many that are in an oil. Now that you know the oxidation reaction, or basically the basic version of it, so what? What does that mean for your oil? I've told about the reaction, but what is it doing? What is it causing? What are the problems it is causing in your oil? Well, this is where the other tests come in. First on this list is viscosity. Viscosity is the single most important property of a lubricant. If you learn about oil analysis in any sort of in-depth way, this fact is going to be drilled into your head. Viscosity is important. It is the resistance to flow, but in layman's terms, you can kind of think about this as thickness. So for instance, water is much less viscous than, say, honey. It flows more easily. It has less resistance to this flow. Now, oil's viscosity does change throughout its lifespan. It can shift up and down depending on environmental factors or chemical changes that are happening, or even just structural changes in the oil itself. But typically, it'll start to increase as the oil ages. Now, this can be problematic, as every single compartment has a specific range of viscosity that it is supposed to operate in. So if your oil gets too thin, moving parts will suddenly start touching each other. It'll start causing wear. And if it starts to get too thick, you're going to have part sticking, increased heat generation, resistance, decreased efficiency. So an increase beyond what is acceptable for any component will have negative ramifications for the equipment as a whole. A big reason for this increase in viscosity comes from oxidation. You've seen the process. Let's look at one of the side effects and what makes oxidation such a big problem. The key to viscosities is a process called polymerization. This process is where smaller molecules bind together to form larger ones with different properties, shapes, and complexes. We can look at a simple example below. Remember these reactive radicals. You saw them before in the oxidation reaction, and they don't always have to bind to oxygen. They can bind to one another. Those free electrons still want to bind to things, and if they come in contact with one another, they can form a double bond. When they form that double bond, it basically ties those two carbon chains together and makes a much longer carbon chain. Now, this creates a much longer carbon chain overall. It's essentially like spaghetti sticking together. The chains will bind to one another, create a new shape, and they will start becoming more resistant to flow. It'll be longer chains, they'll be connecting in weird ways, getting bound up in one another, and this is where that viscosity increase starts. And unfortunately for you, this simple binding that I've shown, where it's just, you can kind of visualize it as a straight line, is not the only kind that can happen. They can be branching, they can form circular structures, and eventually they can form large complexes. These enormous structures can form, which drastically increases the viscosity of your fluid. Given enough time, these structures made out of these carbon chains can conglomerate, oxidize further, and become varnish and sludge. Those sludge deposits and overextended oil are comprised in part by these large bundles of carbon chains. So not only is oxidation creating these large stranded molecules that increase their viscosity, it is also driving the production of varnish and sludge. Now, that is already harmful to your equipment and oil, but that is not the only thing that oxidation does. Remember what I said about hydroperoxides, these carbon chains with two oxygens in the end of them. They tend to be unstable and decomposed. I showed you one option sort of for that decomposition, but there are others. These other forms can typically take the form of acids, some of which I have shown here. Now, even if you're not well versed in chemistry, you kind of know what acids do. They react with metal. Acids react with many different types of metals to form metal salts. And when they do that, it looks like corrosion. It is actively eating away at this metal. For obvious reasons, this is not an ideal chemical to have in your equipment, which is mostly comprised of metal. High acidity can cause corrosion, kickstart other reactions, and continue to contribute to sludge and varnish. In the lab, we measure these acids as acid number, or AN. This is basically a measurement of the total amount of acids present in the oil. Remember, we can't stop oxidation completely, and we cannot stop acid generation completely. So this acid number will still rise throughout your oil's lifespan, but we can combat it. And how we combat it is using overbase additives. These are chemical complexes usually based around calcium, magnesium, sodium, and sometimes barium. If you look at oil analysis reports, some of the magnesium and calcium that you see in your additive package is coming from these additives. They're there specifically to bind to those acids and neutralize them, thus balancing the quantity of acids in your oil. In the lab, we measure this overbase additives, or this alkalinity reserve, with a test called base number, or BN. It's a bit like the reverse of acid number. It can be thought of as the acid neutralizing ability and level in your oil. If you have a high base number, your oil can still neutralize acids. Now, like antioxidants, they are a finite reserve. There are only so many of them that you can cram into an additive package before they themselves start causing problems. As oil ages, acidic molecules are created, the overbase additive neutralizes them, and is consumed. Over time, you will see a decrease as the base number neutralizes those acids. Now, this slide sort of shows how antioxidants, acid number, and base number plays off of one another. There's a little bit of a timeline that goes like this. An oil is put into service and oxidation starts ramping up. The oxidative process starts to produce acidic molecules and acid number starts to go up. Luckily, the oil has antioxidants. Those antioxidants keep the oxidation reaction under control, and the acid number kind of goes up, somewhat stays the same, but it doesn't ramp up. As time goes on, those antioxidants are used up, and they reach a concentration which they can no longer stop the oxidative process as well as they once did. This leads to the oxidation reaction starting to accelerate. It accelerates, more acids are produced, and the base number, which has been working silently in the background, those over-base additives, they start binding to those acids. Base number starts to drop, acid number starts to skyrocket, and those harmful products of the oxidation reaction start to accumulate. Oxidation rises, acid number rises, base number bottoms out, and viscosity rises. This is how the process proceeds normally. But what if there is something in your oil that shouldn't be there? Contaminants throw a spanner into this entire process. What was a nice, easy to understand balance between oil aging and the additives sort of combating that gets completely thrown out the window when a foreign body enters the equation. Abrasives, for instance, such as dirt, you already know they cause immense amount of damage to metal surfaces inside a component. They strip away metal. Abrasives such as dirt can cause massive amounts of damage to the metal surface inside a component. But an often neglected part of this is they can also drive the aging of oil. The metal that it shaves off can become a catalyst for that oxidation reaction. It can cause it to speed up. Also, those areas where those abrasives are coming in contact with metal become temperature hotspots, which can also accelerate the oxidative process. Soot can do a very similar thing. Soot causes hard particles that act like abrasives. Soot can also increase the viscosity, which is going to increase the resistance to flow, decrease the friction, increase the temperature in the oil, drive the oxidative process. Water is the worst one you can possibly have in there. It causes a multitude of reactions and degrades the additives to where they can't do what they are supposed to do. Other incompatible oil can cause problems as well. If the viscosity is too low, again, you have that metal-on-metal contact from parts that are no longer able to separate. And if it's too high, then you're going to have an issue with temperature increases, viscosity increases. And if you have completely incompatible oil, those additive packages may not play nice to one another and can cause the overall degradation of oil. Even fuel can cause issues. High sulfur from contaminated diesel fuel can react in the crankcase to cause the generation of sulfuric acid. Gas engines have to worry about it too, through the formation of nitric acid. Both of these cause acid number to go up, base number to go down, and to overall increase the speed at which your oil degrades. But this is all to say that this topic is complicated. There are many different variables that can affect a fluid's health, and the processes that I've showed you here so far are a simplified version of what is actually happening. Now, we do have lab tests to test this. Monitoring those lab tests from a unit-by-unit basis is helpful for that particular unit. But in a perfect situation, this is the timeline that you can expect. As oil ages, oxidation increases, acid number increases, viscosity increases, and base number decreases. Those are all normal parts of the oil aging process. So, when is the optimal time to change the oil? Ideally, you would like to change it immediately before all of those different test results start to become exponential, before that viscosity starts to rise, before that acid number increases, before oxidation runs away. Unfortunately, it's pretty hard to find that sweet spot. Like we talked about at the beginning, there are many factors that can influence the ideal drain interval, and it becomes incredibly difficult to determine unless you can see your data from a bird's eye view. Tracking your oil aging from a top-down approach is the best way to determine when the ideal oil drain interval is for your entire fleet. Is it guaranteed to be the best for every single unit? No, but it is good as an overall measure of how your fleet is performing. Doing it from this angle, as opposed to unit by unit, allows you to gain an overall average across the entire fleet and reduce the influence of random variables like contamination. Take viscosity, for instance, with the graph on the left. You know that a majority of your oil samples fall within this set boundary. Everything beyond that is abnormal, and you can tell that it starts to have a negative effect on your equipment. This is going to help you determine what limits to work with. Once you have those limits, you can look at the changes over time, like the oxidation graph on the right. You can track those changes in oxidation. You can sort of predict out where they are going to go and see at which hour or mile they are likely to go over those limits that you have calculated. Tracking all these test results changes can help you narrow down exactly when you hit that sweet spot. That sweet spot's going to allow you to extend your oil drain without causing catastrophic damage to your equipment. Like I said, it may not be perfect for every unit, but it can give you a guideline to apply across every fleet. But how can you do this safely? Here's a basic pilot project that I have set up. So first, we want to select some units for your study. These units need to be a representative sample of your entire fleet. If you have 3 different sized hydraulics, you need to include each one of those in the study. If you have engines that run 2 different types of oil, you need to include both those types of oil. They need to be a complete representation. Then you need to go about determining where you currently stand at your current drain interval. Take samples. Look at where the data is right now. Are you already going over your oil drain? Is it already putting too much pressure on the oil? Maybe you can't do this study. Or is this oil look pretty good? It's nowhere near what even the OEM recommends. Maybe you can stretch it out a little bit further. Is there any abnormal wear that is occurring throughout your equipment? These are the things that you have to sort of take into consideration right at the beginning. After this, you need to determine estimated limits to use for this study. These should be conservative. In other words, you do not want to get to a point where damage is already occurring to your equipment. For example, if you know that your viscosity at 110 centistokes is already causing problems with bearing wear, then you do not want to set your limit at that 110 centistokes. You need to bring it back. Bring it down to a level where you're not causing damage. Once you have those in place, now it is time to slowly extend your drain. You can do this in small increments. The increments are up to you. It is fully dependent on what you are comfortable with doing. It can be small, like 10%, or you can jump a little bit further than that. The important part is watching those increments and seeing how the oil changes over time. You can track this oil over time as you extend the oil drain, and you can start to see where the oil becomes an issue. Once it starts becoming an issue, then you can backtrack and set a time of your choosing as the new drain interval. Now you're ready to start slowly rolling it out across your fleet. Once you've got this ideal drain interval set in stone, you have to keep monitoring your oil. You'll probably need to adjust the sampling frequency, as no matter what you do, you are incurring a bit more risk just pushing it out as far as you have. Sampling your oil will allow you to keep an eye on each unit individually and make sure they are holding up with this new interval. And again, this is just meant to be an example. It's not the only way you can accomplish that. This design that I have here is meant to minimize risk, be driven by real data, have multiple fail-safes, and be in control for multiple variables. Beyond this, if applicable to you, you could even move on to condition-based oil changes. Now, this one is not right for every compartment and company, but if it is done effectively, it is the most cost-effective way to perform oil changes. This setup is somewhat similar to a regular oil drain extension. The big difference here is the endpoint. At an ideal drain interval model, you will still drain at set intervals. Once you've moved to a condition-based system, though, you will only change the oil if the analysis shows the oil has gone over our calculated thresholds. You'll still need to roughly establish where this is going to happen and have maximum allowed time on the oil to mitigate risk, but if performed correctly, this is the best way to manage drain intervals. Let's look at an example of what one of these kind of projects looks like. Now, a client has been on a simple oil drain interval for many years, but wanted to experiment with a condition-based system with sort of an upper-level oil drain. They selected roughly 100 units for this study. These were comprised of only the specific kind of unit that they wanted to extend this drain interval for. And they started tracking the oil health results over their current drain interval. Once the initial data was collected, we were able to deduce that their current drain interval, the oil was not really being put under any stress that it couldn't handle. And we could actually extend the oil drain interval. Setting up the sort of conservative limits we used was pretty tricky, but through a combination of OEM recommendations and data gathered on the fleet, we were able to come up with limits for the fluid tests that, we knew would not harm the equipment. The next step was slowly extending the drain. Starting small with only extending it 10% each drain interval, increasing once we were sure that the limits weren't being reached. Over time, the trend is what you can see here. This is what was established. Using this method, we were able to extend their drain interval by double what their original one was. Once the project is complete, they will have a maximum allowable drain interval, which is shown here, and they'll be using condition-based monitoring throughout the drain interval to make sure that if that oil wears out prematurely, they know to change it before it hits that level. Now, this approach may or may not work for everyone, and the results may not be as dramatic as they are here, but this is the potential power in doing a study like this. Every company is unique. Everyone faces their own specific challenges and pressures, but taking an approach like this allows for you to account for those pressures and dial in on the perfect drain interval for you. So, to summarize, if you are wanting to extend your drain intervals, here's a brief checklist to follow to keep your equipment safe. Figure out what variables will impact your oil, whether that be environmental, fuel type, compartment type. Check with their OEM guidelines. They built and manufactured this stuff, so they probably know what is concerning as far as test results go. You have to establish a quality sampling program and monitor it. Gather that data on the current drain interval. You have a set drain interval already, gather data. Establish a quality sampling program and monitor it. Gather data so you have something to use as a baseline. Established a controlled study with the help of oil analysis provider to try and extend your drain interval. Monitor your oil analysis results and proceed cautiously to reduce overall risk. And continue monitoring even after you've found your ideal drain interval. Just because you've extended it does not mean you should quit sampling. On the contrary, it's even more important now. Finally, if it works for your particular situation, consider switching to a condition-based monitoring. If you are interested in performing a drain interval study with us, please feel free to reach out to our labs and get paired with a consultant that will take you through this process step by step. Thank you.